Welcome back. We are still doing electrochemistry and oxidation reduction reactions. This is chapter 19, and this is part 2 of the lecture. First part of the lecture, if you'll remember, we did oxidation terms, oxidation chemistry in general, and balancing redox reactions. Now what we're going to do is take that knowledge of oxidation reduction chemistry, where electrons exchange between species, and what we're now going to do is talk about why we can use those electrons and produce electricity, basically from a battery, okay? So this will be voltaic and galvanic cells. Two historic terms, two good workers in the area. The terms are used interchangeably, but we're talking about the same chemistry. So we'll talk about what a cell is, and then we will talk about how do you determine what the spontaneous direction of a reaction is. Okay, it goes back a little bit to Chem 1B and thermodynamics. You'll remember there's in a mixture one direction that's spontaneous, and the reverse reaction or direction is not spontaneous. Obviously, if we're building a battery, we're interested in the spontaneous part. Okay, so let's talk about how a cell would look if we built one in the lab. Now, to be consistent, let's stay with the example that we started with in the last lecture, which is the copper zinc system. If you remember, in that system, first real slide, we had a bar of zinc we put into a copper solution, and we had a reaction, okay? Electrons were exchanged. And we saw a picture something like this, although not exactly like this. And the electrons went directly from the zinc to the copper. So we may have gotten a product we were interested in, but we never held the electrons in our hand. We never had them flow through a wire. That's what we're going to try to do now. We're going to try to get those electrons to do what we want them to. We want them to go through a wire, and we want it to go where we want it to go, do what we want it to do, and then it can go home and rest, or they can go home and rest, okay? Now, by do, that could be anything from lighting a light, running a cell phone, a computer, anything electrically powered at all. So let's look at how a cell would work. And what we're going to do here is follow the electrons. Now, if you think about your wiring or the wiring in your house, you flick a switch, the light goes on, you flick a switch, the light goes off. What are you doing when you flick that switch? You are completing a path so those electrons can go through a full cycle. If it's broken anywhere, any of the wires cut, switch off, you name it, the circuit, the battery will not work. So let's go through and spend some time understanding how the electrons flow in a cell. Now let's start over here with the zinc. Now, the zinc, and I'm not going to explain why things occur the way they do now. We'll do that a little bit later in this unit. Now, in the anode, which is where electrons come from, it turns out electrons freely or relatively freely exit zinc. They will take off and leave a zinc +2 ion, okay? So we have the zinc atom, the electrons go up here, up in the electrode, and that zinc 2+ is probably toward the outside of the bar on the surface. And what happens is that 2+ becomes unstable, It interacts with the water. Remember, we talked about solutions a couple chapters ago? That's what the zinc ion does. It surrounds itself by water. The electrons are the lone pairs on the water, complex the zinc, they bind to it. So the zinc 2+ is more stable in the water solution. So we now have electrons going around. We go here, it says through a voltmeter. Now, again, that could be a battery, not a battery, but a light bulb or something. So what happens? Those electrons go through, they do the work we want them to, whether it's allow us to take a voltage reading or shine light or whatever. Then the electrons keep passing on and they go into what's called the cathode. It's a little bit like going home, okay? So those electrons, in this case, because we're talking about the copper zinc system, the electrons flow into a copper bar. Okay, now those electrons will gather around the copper bar up to a point. Once you get so many electrons, you can't get any more in because they obviously repel each other, right? So where do those electrons go? Well, on the cathode side, we need a place to store them. And it turns out that place is on copper 2 ions. So those copper 2 ions, as we see here, they will come to the surface of the copper bar. The electrons will flow through to the copper 2, and that copper will be reduced, right? Okay, so once it's reduced, in this case, what would we see here? We would see a dark coating coming out on that copper electrode. Why? Because it's not copper metal that's been melted in pure metal, it's those nanoparticles we talked about, okay? They do stick together, but it's not the same thing as pure copper metal that has a well-formed lattice. All right, so now as and we're just going to go around the circuit here and talk about this. As we remove the copper, what do we have left? Well, the copper had to have an anion, correct? So it could be chloride, nitrate, any one of a number of non-reactive anions. So as we remove the copper, the electrons come in, we remove it, we start building up anions. Now, at some point, we have electrons on the copper, electrons or anions in solution, so that copper has to make a choice. Does it go to the electrode, or does it stick around with its anion buddies? Okay, which means if you have a copper ion over here toward the left side of this beaker, and there's a lot of anions, it's going to be hard to get that copper 2 to the electrode, which means what? We have too many electrons, which means the electrons are going to have a hard time flowing over, and our battery won't work well. So what do we need to do? We need to get rid of the anions or find another way to neutralize those negative charges. Now, it just so happens there is a connector in a battery, and in these lab situations, it is called a salt bridge. And what you have is, in theory, an inert salt. In other words, it does not impact the other battery chemistry. So in this case, we have sodium sulfate. So if we have too many anions here, what do we have come out here? Well, certainly not the sulfate. The sodium would come out. The sodium, this is going to be in a paste or a concentrated solution. It will be in some form that permits the ions to flow, both the cation and anion. So in this case, to counter the anions on the right, Sodium will come over, neutralize the anions, which frees up our copper to now have an easier time. I'm not saying easy, but easier time coming over to the electrode and being reduced. Okay, so we have sodium coming over here. And now let's jump over here to the anode side. Now, so if you remember, I said the zinc 2+ concentration will build up as we remove those electrons. Okay, so this is increasing. Well, we obviously are going to get to a point where we have too many cations in solution here, not enough anions. So what happens with the cations? Well, we have electrons here, right, that haven't flowed out yet into the circuit. So these electrons are going to attract the cations that are in solution. Well, the more cations come over here to hang out around the zinc bar, the less likely we are to have electrons flow through. So what do we need there? Well, we need an anion, right? Do we have an anion in the salt bridge? Yes, we do. So what happens here, while the sodium is going this way, meandering over here to the copper, on the other side, the sulfate flows over or wanders over and counteracts the charge on the zinc. Notice we have a full circle, okay? We have, let's say we have 100 electrons. It leaves here, okay? That means we have 2 electrons per zinc, so there should be 50 zinc ions in solution. So the 100 electrons light our bulb for a little bit, get rid of some energy, then they continue to flow over to the copper. The copper wants the electrons, okay? So how many coppers does this reduce? It will reduce 50, okay? 100 electrons, 2 each, makes sense. So then we have what? Depending on what the anion is. Let's say it is chloride, okay? So if it were chloride, then we would have how many sodium ions coming in? Well, we would have 100 chlorides, meaning we would need 100 sodium, right? 100 sodium matches up with 50 sulfate, right? So that means we have an excess charge of 50 sulfates or 100 negative charges. If 50 sulfates flow into the left-hand beaker, the anode, what do we have? We have a neutral solution, 50 zinc ions and 50 sulfate. So everything matches. And as long as we build the battery right, this will give us a continuous flow until we either run out of zinc ions, well, not ions, but zinc metal that we can oxidize, or copper 2+ that we can reduce, okay? That's what we're trying to do. We want to have some way to have the electrons go here and do what we want them to, okay? So that's going to be the purpose of this particular topic. Okay, now, a couple terms that we want to make sure we understand. We used them in the last slide, but let's be a little more specific. If you remember, up above on the zinc side, we said that was the anode. It will always be by standard notation. It will be placed on the left, and it is the oxidation half cell, meaning it is the species that loses electrons, and it is always called the anode, right? Now, on the right-hand side, we had something called the cathode. By our standards, or standards that have been developed years ago, that is called the reduction half cell. And that will be the species that wants the electrons. Now remember, we are talking about copper and zinc. So in this case, copper will want to be the reduced, okay? Now, it depends what we match that with. If we match copper with maybe like silver plus, take my word for this, the silver plus will then replace the copper. So the copper, if it was a copper silver system, silver would be here at the cathode, and the copper metal would have to be the metal, would be the anode. Okay, so it's relative to their ability, the pair's ability to be oxidized or reduced. Okay, now salt bridge, that is what completes the circuit. It's like our switch. Okay, once that's in there and it's working, everything should be fine. Now, what we have to make sure is that the electrons cannot take a short circuit or a shortcut. And what I mean is, those, if we were to take those two beakers and put them together and mix the solutions, the water or the electrons would go directly across, and we wouldn't get the electrons coming out, going through the wire and doing what we want them to, okay? So there is an art and a science to the salt bridge. Now, as we said before, the cations in the salt bridge flow toward the cathode, and the anions flow to the anode, okay? Pretty easy, but we just need to make sure that we are using the terms consistently. Now, staying with the zinc copper system, this is the equation. I don't think we'd have any arguments that that is the chemistry that's occurring. Well, one of the things we would like to do is to be able to have like a notation that we could use. So instead of drawing this diagram, we could put a little, well, not call it equation, just notation that will allow us to reconstruct what we have up here. So what we do is we start, and this is just a general equation. All it says is essentially, this is what's occurring, but it tells us how to build the circuit or the battery or the cell, whatever you want to call it. So up here, we would say that we have the anode, the metal itself, and that is indicated by zinc as a solid. And to show that there's a difference in phase between the metal and the solution, we put a bar. So when we look at the left side, we can say, there's a bar of zinc in a zinc 2+ ion solution. And that's what we have. Now, to go to the right side, we have what? A copper solution, okay, copper solution, and in with the copper solution is a copper bar or electrode. So we have another bar here, and we have the copper solid. Now, to separate these two beakers, we put a double line in. That basically indicates the salt bridge, okay? So a salt bridge is, in this case, and for our cases, is just a bridge, and we are not going to really specify the salt that we use in the bridge. We use sodium sulfate in the first example, but it could be any one of a number of salts, okay? It could be sodium nitrate, it could be potassium nitrate. Now, we are going to make the assumption that the salt bridge composition does not matter as long as it does not interfere with the chemistry that's going on. In other words, it's like a net ionic equation. The ions are there, but they do not participate in the chemistry. Okay, so this is the general equation we would write. Now, what happens whenever we start comparing batteries? Well, it turns out you need to have a standard. You remember when we did thermodynamics, we said there's a certain set of standards. Room temperature, 1 molar solution, 1 atmosphere pressure, if it's an element, standard state of the element at that temperature, okay? Well, that's how we measure voltage, or how much power or energy the battery can produce. And that's called standard state. And a lot of the standards are exactly the same. The temperature is room temperature, 1 molar solutions, and 1 atmosphere if a gas is involved. We'll talk about that later. Now, whenever we look at the standard state, and to indicate the standard state, that is what we're talking about. So if you do an experiment in your lab, or I do one in mine, and we say standard state, we both know exactly what we're talking about, okay? And those values for the cell or battery should match, values mainly being the voltage. So in this case, all we would change, we would have the same information here, except now we would say the specific concentration, 1 molar and 1 molar. Now, let's say we have a reason for doing something other than 1 molar or 1 molar. We have a way of making the battery last longer depending on what we put in at what concentration. And there may be a cost factor involved. One of the components is expensive and we don't want to use a lot of it. So we optimize the other components around it. And one example might be, is for a non-standard battery, we say we have a zinc solution that's 0.5 molar and a copper solution that's 0.2 molar, okay? And it could be anything that is non-standard, or I should say non-standard is anything here that is not 1 molar, 1 atmosphere, okay? Okay, this is some information. This is out of your textbook. No need to go through that. Now let's take a little more sophisticated example. And actually this chemistry should look pretty familiar. If I'm not mistaken, we balanced this equation last time we talked. Okay, so if we have we'll call it a proof of concept cell. This is actually a battery formation or formulation that can be used, okay? But it's not a commercial battery. This is our laboratory battery. So let's look at what we have. We have an anode here, which is carbon, and we have iodine, I2, and we have I- in solution. Well, let's look at the chemistry that's occurring. Now, in this case, we have 2 I- in solution, and that's where the electrons come from here, right? We are taking those 2 electrons from the I- or the 2 I-, and we're forming I2 solid. Now, I2 is a little soluble in water, but not much. So what happens is that I- iodide comes up, donates the electrons, combines, and you end up with the iodine coating out on an electrode. Now you need something that will pass electrons. You can flow the electrons through, but it needs to be cheap, okay? And in this case, there's something called glassy carbon or graphite. Not exactly the same thing, but for our purposes, pretty darn close. Bottom line, it conducts electricity, or they conduct electricity. So for the anode half reaction, we would write this, it's balanced, okay? Now, that it means we have electrons flowing over to another carbon electrode. And what do we have there? Well, in solution, we have permanganate, acid, and then we have manganese +2, and we're forming some water. So let's look at the cell here. Okay, that is soluble, the permanganate, so that's shown in solution. We have acid that's present, that's shown in solution. And then we have the product is shown in solution, the manganate +2. And notice we don't put the water in. It's the solvent, so that's irrelevant here. So we do not write that in special. This is all water solution, okay? Now, if this was a non-aqueous system and we formed water, then we would add that, but we're not going to worry about that here, okay? So we have two half reactions. And remember I said there was an advantage to having the half reaction method? You knew what was happening at each electrode. So if we look at the overall equation here, maybe bump that up a little bit, we notice that we have the permanganate and the iodide on the same side. Well, they should be. And we have the acid. But it's not clear as to where that acid would really be. Is it in both solutions? Is it in one? Well, that is what we can figure out here. We can say, okay, if this is the anode half reaction, then we can write the half cell, which is split at the salt bridge, right? And we can say, okay, what is our electrode? In this case, our electrode is the graphite or glassy carbon. And it could also be something like platinum. Platinum is an excellent electrode. The problem with it is extremely expensive, okay? So graphite, when possible, would be used. So on the left-hand side for the anode, what do we have? We have the I- solution. Now, remember I said between the graphite and the solution, we have 1 bar to show a phase difference, okay? Why do we have a bar here? Well, it's because we have another phase difference, right? Notice that I2 is on the graphite. It is as a solid, okay? So this says I have a graphite electrode. I can vision that. I have I- in solution, and I have I2 that's sitting on the graphite electrode. Then I have that container or portion separated by a salt bridge from the cathode half cell. All right, so cathode half cell, what do we have? We have the graphite, obviously, graphite in a bar. And do we have anything here in the cathode half reaction that is not in solution? No, we have 1, 2, 3 species, all in solution, and that's what we have written here. Okay, now notice in this case what we have, the order in which they appear is the order in which they either are as reactants or products. I don't know that there is a hard and fast rule that says the manganese 2+ has to be on the right side. I tend to write it that way just because it's easier for me to correlate this notation with the half reaction, okay? Okay? All right, now, I am not going to cover this, but whenever, if you want, get a screenshot of this or just look it up on, like Google it. And this tells, it's a fascinating and an interesting material, but it talks about making carbon material that is pretty highly conductive, okay? Also, just for your information, Graphite, you can layer it in sheets. It's like if you have a pencil lead, that's graphite. And when you write and you see that black mark, those are thin sheets rubbing out or coming off, sheared off, and they attach to the paper. Well, there are several groups that are looking at the electronic properties of those thin sheets of graphite, and they are able to make what we call molecular transistors out of those materials. It's not commercial yet, but it is a fascinating area of technology. Okay, now, so far we have talked about, and we're going to stick with, the copper zinc system. What would it look like in a cell in beakers in a lab? How would you write notation? Okay, but if you remember, whenever we showed the first slide, we said not only are we going to talk about the cells a little bit, we need to be able to determine which way is spontaneous. That way we will know which half reaction is the anode and which half reaction is the cathode. Okay, now this table, this is from your textbook, okay? And if you look in your textbook and see it, you will notice I trimmed off some information over here. And I did that intentionally. It's basically what the voltage of each half reaction is, okay? But I did that intentionally because I don't want to think in voltage now. I want you to be able to qualitatively determine and be confident that you have selected the proper way in which the reaction will go to the right or to the left as written. Okay, so let's say, and I probably could have combined this slide with the other one, but either way, this is a little bigger here. So, okay, so what do we have? We have an equation. Now, stick with me on this because I know you already know the answer based on what we've discussed. But we have been assigned to look at a copper zinc system, okay? Our boss comes in and says, you will work on this. Now, copper zinc, that means if we look at these two metals, copper, if it's a battery type situation, depending on which way it goes, we either have copper going to the ion or the ion going to copper. Okay, so let's look down here and see what we have. Okay, there's copper 2 going to copper. Okay, so that makes sense. Copper and copper 2+. And then we have zinc. And we look at zinc here. Do we have zinc? Yeah, 2+ going to zinc metal. Okay, so we now know, based on this table, that in both cases, the ions that are produced are in the +2 state. Now, I want you to notice that everything we have written is in the state where we are taking the species that would be the oxidizing agent. In other words, it's being reduced, and we're adding electrons, and then the reduced product or the reduction product is on the right. Now, let's think about this. Now, this is written intentionally for standard form, okay? In other words, everything we write as a reduction. So if we think about fluorine or chlorine, those are pretty darn strong oxidation agents. We know they go spontaneously. We would not want to breathe it. We wouldn't want to get it on our clothing, our hands, on our lungs, nothing like that. It's potent stuff. So that means if we look up here, strength of oxidizing agent, top one here is fluorine. Now, as we go down here, you will see that some of this it really doesn't make sense as we get down here. Now, think about sodium metal or lithium metal. Do they want to gain an electron? So if you throw lithium plus into a mixture, does it want to go back and form the lithium metal? No, not in most cases. Now, can it be done? Yes, but not under normal conditions, okay? So that means if we look at all these species that we say are oxidizing or potential oxidizing agents, we go from very, very weak to very, very strong. So the higher up on this side we are, the stronger the oxidizing agent. So now let's go to the other side. On the other side, these are all reduced species, okay? So these now are called reducing agents. In other words, how credible or how feasible is it to expect these materials to want to be in a reaction and give up an electron or two or three? Well, if we look, strength of reducing agent increases toward the bottom. That means lithium should be one of the strongest reducing agents we would have. It really wants to get rid of that electron. So it wants to go this way, just the way fluorine wants to go the other. So as we go up, the reducing strength decreases. Okay? Makes sense? Now, let's go back to our example. We have two metals, and the metals are all going to be on this side. So what do we have? We have copper and zinc. So what we want to do is compare which one is the stronger reducing agent. Okay? So we have, there's copper and there's zinc. Okay, copper and zinc. So which one is stronger? Well, obviously zinc wants to get rid of the electrons more. So that should be our anode, right? And that means copper will probably be the product, okay? Now, let's look at the ions. We have zinc +2 and copper +2. Which one is the stronger oxidizing agent? Well, obviously copper 2. So that tells us on the left side, we have the strong oxidizing agent and the strong reducing agent that will react and form the weaker copper reducing agent and weaker zinc oxidizing agent, okay? Now, that means just like whenever we did acid bases, we had a similar table for the acids and bases. Strong and strong react, weak and weak form, okay? That means we could then with confidence say the zinc metal and copper 2+ would be on the left side, the copper metal and the zinc 2+ would be on the right, and that would be the spontaneous direction. Okay? Now, this is just a little bit of an explanation. It's the same thing we just went over. If you want to get screenshots of it when you watch this, that is fine. Now, let's take another example. Let's say that we have a cell and it's not obvious. Well, maybe not as obvious. And we say the cell is combined, or it's a combination of zinc and iron and their counter ions or associated ions. Now, what we would like to do is be able to determine what is the spontaneous direction and then sketch the cell layout so that we could say this is how we would build it in the lab. And then we would put in notation to let everyone know that the solutions are all 0.5 molar and that we have a sodium nitrate salt bridge. Okay, now we have silver and iron. So let's go back up to our table here. Okay, so we have silver and iron. So let's start with that. Well, there's silver metal and there's iron. So what does that tell us? That tells us the iron solid should be the reducing agent, meaning it will be the anode. That would be the electrode that we would use in the anode, okay? Now, for the cathode side, what would we have? Well, it would either be iron +2, which we already know it's not, or silver 1. All right, well, which is the stronger oxidizing agent? Well, obviously, silver +1, meaning that it wants the electrons that the iron is ready to give up. So it will grab these electrons from here and give us the silver metal. That's what will code out on either a silver electrode or maybe graphite again. And what we're left with on the anode side is the zinc ion in solution. Okay, so let's go down here. Let's go back to our other question. And let's look starting here at the equation. So what do we have? In the balanced form, since we're losing 2 electrons from the iron, we need 2 silver plus ions to accept those electrons. So 1 iron, 2 silver, 2 silver. So if we draw the cell, in fact, well, let's just do this up here first. Okay, we know the anode is going to be an iron. We know that iron solid, or the iron solid is here. It's going to form iron 2+ in solution. Okay, we could write that here, and we know it gives up 2 electrons. The 2 electrons come over here. Cathode will either be, as we said above, silver metal or graphite. So that means we will have silver +1 in solution, and it will take the electrons and form silver on the cathode, solid cathode. Now, writing that in form here, just the general form would be to say we have an iron anode, we have iron 2+ in solution, we have a salt bridge. In this case, we're not specifying the ion, or the salt, I should say. And then in the cathode side, we have the aqueous solution of the silver and the line, the bar, and the silver or graphite for the electrode. Phase changes, salt bridge. Now, remember we said we actually wanted to do 0.5 molar. So it would be iron. This solution, we would change the read 0.5 molar, and the same for the silver. Okay. Now, again, we mentioned this earlier. We are ignoring the sodium nitrate. It's assumed to not be material in terms of impact the cell. Not strictly true. It can have an impact, but we are going to assume it does not. All right. Now, lastly, what I want to do is go over some terms with you. Now, we will use these throughout the rest of the chapter. We're not going to go into depth here, but I want you to be aware of them and be thinking about them. So whenever we come back to them, you'll at least say, well, I'm not sure what it is, but I've heard of it. Okay? So what we are going to be looking at for the next lecture is something called the cell potential, E subscript cell. It means the voltage that will be generated across the anode and the cathode that we can use. It's like your car battery generates 12 volts, and that's what is used. That voltage, along with some current, is used to start your car. Okay, now, whenever we talk about a cell, we either refer to this as the cell voltage or electromotive force. They are both essentially the same term. I think if you're a physicist or an engineer, you may use EMF sometimes in some applications more than voltage, but it really doesn't matter. Now, for the spontaneous side, whenever we talk about a cell, and we talk about copper, zinc, what do we have? We will have positive and negative voltages. A positive voltage, one that's greater than 0, indicates the process as written is spontaneous. It goes, if we have it written, this is the anode, that's the cathode, that's the way it will flow. If for some reason you have a drawing with what looks like an anode and a cathode, and somebody said, well, that cell generates -3 volts. Well, then you know that somebody crossed up the two half cells. The cathode is actually the anode and vice versa, okay? So let's just touch on a couple other terms. Now, the ampere, you've probably heard of amperes or current. A is the term for ampere or the symbol for ampere, and it is defined as 1 ampere is equal to 1 coulomb per second. 1 coulomb is a unit of charge. And what it comes down to, this was tested and found, well, roughly found in the 1800s. This is old terminology, even before they came up with or found that the electron really did exist. They didn't know what it was, but they knew there was something going on there. So it's out of that, that's sort of a historical perspective, very little perspective. So if we say 1 ampere is 1 coulomb per second, that is the same thing as saying we have about 6 times 10 to the 18th electrons passing a point per second, okay? So whenever they found the coulomb, later whenever they said, oh, holy mackerel, we have electrons, then they figured out this is the charge on the electron. So for the 1 amp of current, this is how many electrons are involved. You can think of it like water flowing in a pipe. Same thing as electrons flowing in a pipe. So if you have water flowing in a pipe at 1 gallon per second or 15 gallons per second, that is equivalent to your current, okay? Now, the coulomb, here is a more formal definition. I'll let you read that. And we'll be using coulomb quite a bit later. But again, this is not hard. Once you see it and use it a couple times, like oxidizing agent versus reduction, that type of thing, it'll fall into place. And then a volt. That is defined as 1 volt is equal to 1 joule of energy per coulomb. So that would be the same thing as saying 1 joule of energy over 6.2 times 10 to the 18th electrons. Okay, so that is how much energy we have. Okay, so if I said 15 joules, that would be 15 volts. So that's 15 times more energy than 1 volt. So each electron at 15 volts would have 15 times more energy than that electron would have under 1 volt. Okay, now what we can think of here is this energy is like water pressure. So you can have 1 amp flowing, so many gallons per second, okay? And in volts, it's water pressure. You have 1 atmosphere of pressure, 10 atmosphere of pressure, or 1 pound per square inch, or 10, 15 pounds per square inch, okay? So think that over. We will address them again. Well, we're going to more use them again. This isn't a theoretical course, so we're not going to derive that type of stuff, but you will need to understand it enough to be able to use it, okay? Now, next period or next class, next lecture, part 3, what we're going to focus on is how to experimentally determine the cell voltage. Okay, we did this is greater than that, this is more strongly reducing or oxidizing, but where we would like to be is to be able to say this battery supplies 1.5 volts. This is what it means. And then how do you compare a lithium battery to, say, an alkali battery? And that can be done, and we will talk about that next lecture. Okay, thank you, and I think that's all for now.